Hi everyone, welcome to another tutorial on LSAT. In today's video, we'll look at the curious case of the z-test. The z-test is one of the most common and simplest formulations to understand hypothesis testing. We'll cover it as an example to understand the basic idea behind hypothesis testing. As a part of that, we'll begin with a simple data distribution. So this is the graphical representation, let's say, of a data distribution. We'll not worry too much about the specifics of the distribution. It could be any distribution. And once we have a distribution, remember that the central limit theorem, if you've seen the last video, or otherwise if you're well aware of the central limit theorem, remember that regardless of which distribution you begin with, as long as you take samples, and these samples need to be of a large sample size, preferably 30 or greater. And if you keep taking these samples repeatedly in a random manner, such that the data distribution is equitably represented, you will notice that this will eventually lead to a Gaussian distribution, the distribution of the means of these samples. And that is the fundamental reason why the starting distribution doesn't matter as long as you take samples of a large size. So beginning with that, our next part of the concept of hypothesis testing would be to then select the critical point. So what's the critical point? The critical point is an assumption. The critical point is that point beyond which we say that now the sample is so extreme that we will not go ahead and take the original starting idea as correct. In other words, the sample that we've taken is so extreme that the basic idea is kind of nullified, or your starting idea is nullified. So that's going to be a critical point. Now, what can this critical point be? Well, remember that the critical point can very much be any value, and it can be any high value. So the most common critical point that you will see comes from the level of significance. The level of significance is, think of it as the margin of error that you're willing to accept. So generally speaking, that margin of error is taken as 5%, which is it's nothing but think of it as the probability that something is a part of the distribution, but you're still going to reject it. It's usually taken as 5. And when the level of significance is 5%, your critical point will lie at about 95%. In this diagram, you see this. If you see this red colored vertical line, it kind of separates the entire distribution into two parts. The red colored line representing your critical point. What you have beyond that critical point, the amber colored region, is going to be the area of rejection, and the green colored area is the area of failure to reject, basically. Please bear in mind that some texts or some articles might call it the area of acceptance, but to be technically correct, this is not the area of acceptance. It's purely the area of non-rejection, the area where you are unable to reject the starting idea or the null hypothesis, as it is often called. Another word of caution, remember that 5% is just the most commonly taken value. The level of significance could also be 1%, in which case this red colored line would probably move closer to the edge and would represent, and then this green colored area will cover a larger portion, and the amber colored area will become less. So basically, if you go ahead and select a 1% level of significance, you will notice that your area of rejection is going to shrink or become reduced. So once you have the critical point, you will notice that your distribution is kind of split into two parts: the area of rejection and the area of non-rejection, or the area of unable to reject. Another caveat here is, remember that you can have double-tailed or single-tailed test. For simplicity of visualization, I've just made a single area of rejection. But if your problem is a double-tailed test, means it can basically fail in two different ways, then you might very well have two areas of rejection also. And it is basis the number of areas of rejection is what decides whether it will eventually turn out to be a single tail test or a double tail test. Okay, so let's say you have reached the point where you have the critical point, you have identified the areas of rejection, the areas of non-rejection. What next? Well, the next thing is to calculate the z-score of the sample mean. So remember that you're trying to estimate or trying to see what the mean or the average of a certain population is. You want to compare it with a number. You believe it's at a certain number. You want to check if that belief is correct, if that core idea or that null hypothesis is correct. So in order to do that, remember that you will take a sample. This sample will be randomly taken from the distribution, and then you will calculate the z-score of the sample. So how do you calculate the z-score of the sample? And the answer to that lies in how do you calculate the z-score of anything? Well, the z-score is nothing but the distance of a certain data point from the mean as measured in terms of the standard deviations. So for the sample, remember that it will be nothing but the average of that sample, which is here represented as x bar sample, minus the mean of the samples, right, divided by the standard deviation of the sample. So this is going to give you a z-score, and here we're going to represent that z-score as a black colored dot, as you see here. So now that you have that black colored dot, or you have the z-score of the sample, if that black colored dot lies in the amber colored area, which is it lies in the rejection region, I'm sorry, then in that case we will reject the null. If on the other hand the z-score that you've calculated lies in the region of non-rejection, which is the green colored area, then we fail to reject the null. Okay, so this is the central concept behind hypothesis testing. Okay, just let's do a quick recap. So one, identify the areas of rejection. Second, calculate the z-score of the sample that you've taken. Third, check if that z-score lies in the area of rejection or in the area of non-rejection. Fourth, if it does lie in the area of rejection, then we reject the null, which means, in other words, we will endorse the alternate theory or endorse the alternate hypothesis. And if it does fall in the area of non-rejection, then we're going to stick to the null. In other words, we'll say that, yeah, we have failed to reject the null. We'll stick to the null. We can infer that the null statement or the starting statement is correct, right? So one word of caution again in regards to this. Remember that you're not proving the null or you're not disproving the null. Okay, so please stay away from stating that using hypothesis test you proved something. All that you can say is that you can infer something, you can conclude something, you can reject or fail to reject something, but you can't prove it. It's a statistical test that we're conducting here. Okay, so this is the central core principle behind doing the hypothesis test. So now let's delve a bit deeper into the z-score calculation of the mean. Remember, one of the key steps is calculating the z-score of the mean. So this formula, if you notice, has got three parts to it. Okay, so what are those three parts? So first part is the mean of the sample. Well, this is the easiest part actually, because when you take a sample of 15, 20, 30, 35, and I'm just saying these numbers, you will take a sample greater than 30, right? 30 or greater than 30. If so, it's the simplest part is calculating the mean of the sample, which is just calculating the average of whatever sample you have extracted. The next term to look at carefully is the mean of samples. Now, you can't really calculate the mean of samples in all cases, because it can be a very exhaustive list, especially if the size of your samples, or that's the number of data points in a sample, starts increasing. You can have progressively larger and larger number of samples to look at and calculate the mean of. So what do? We'll look at that in a short while. The next term that you want to look at is the standard deviation, which is the term at the bottom, right? So again, remember that if you can't calculate the mean of samples, you can't also calculate the standard deviation of the means of samples, right? It's the same problem because you don't have all the means of all the samples, right? So we have the same issue in this case. Okay, so having said that, remember that the way out of this problem is, if you recall the property of the means of samples, remember that the means of samples, the mean of means of samples is equal to the mean of the entire population. I think we did cover it in the last video as well. And then the standard deviation of the mean of samples is nothing but the standard deviation of the entire population divided by the square root of the size of the sample. The derivation of these is not in the scope of this video. Maybe we'll cover it in another video, but for now these are the two important things. So how does this help us? The way this helps us is that, remember, you're trying to prove a certain core statement about the central point or the average of the distribution, and that's going to supply the value for the mean of samples. And the standard deviation is something which is going to be assumed as known from historical data, and using that we can then run the z-test. Okay, so let's go on to the actual mechanics of this with an example. So here's a problem statement. So let's say a town council states that the IQ of schoolgirls in the town is less than or equal to 115. It also states that the standard deviation of the schoolgirl's IQ is 15. And then, in order to test this assertion that the IQ of the schoolgirls in the town is less than or equal to 115, what is done is that a sample is collected. So basically, IQ is measured of 30 schoolgirls at random. That becomes our sample. And here, from row number 11 onwards, all the way till row number 40, you have the IQ of those 30 girls who were selected at random, and their IQ was collected. Okay, the level of significance has been set as 5%. Now what we have to do is we have to use the hypothesis test to infer, to conclude, to reject or failure to reject the null, to see if this statement here of the town council seems to be accurate, that the IQ of the schoolgirls is less than or equal to 115. So what is the null hypothesis? The null hypothesis is this statement right here. This is what the town council is stating, right? So this is our null hypothesis. Okay, so we can state that IQ is less than equal to 115. Okay, so this then becomes our null hypothesis, right? This is our starting hypothesis. Okay, what will be the alternate hypothesis? The alternate hypothesis will then be that the IQ is, we'll say that the IQ is greater than 115, right? This is the alternate hypothesis. This is the alternate hypothesis. Okay, so let's begin with this. What you'll notice in a lot of hypothesis testing is that generally the null hypothesis is some kind of an equality, and the alternate hypothesis will be some sort of inequality or greater than or less than values, generally speaking. This concept, by the way, is not just true when you're doing a hypothesis test of, let's say, a population mean against a fixed number. Like in this case, we're trying to test if the population mean is less than or equal to 115. So this concept of the null hypothesis generally being some sort of equality is also applicable when you look at more complex example. Let's say if you were trying to test the IQ of schoolgirls from two different towns, and if you collected samples of 30 each from both the towns and you're trying to compare them, even in that case, bear in mind that the null hypothesis will be some sort of an equality statement, generally speaking, and the alternate hypothesis, sometimes also called H1, it can be H1, it can also be called H subscript A. The alternate hypothesis will be generally some sort of inequality. Okay, so having said that, how are we going to apply it? So one of our first steps is to first of all calculate the sample mean. So the sample mean is the easy part. You can just take the average of these numbers right till the bottom, and here we are. We have the the sample mean. So for this sample that we have taken of 30 schoolgirls and their IQ, we see that the average or the mean of their IQ is 119. Then what we need is the population mean. In this case, the assertion of the town council, as you can see, is that it is less than or equal to 115. So the population mean is going to be 115. Now, what is the population standard deviation? Now, the population standard deviation is given in the problem statement. It says the standard deviation of the schoolgirl's IQ is 15, so it's taken as 15. What's the sample size? We know that the sample we took is 30, so that's our sample size. And now we come to calculation of the z-score. So what is the z-score going to be? Now, in this case, the z-score is going to be nothing but the sample mean that we have minus the population mean of 115 divided by the standard deviation of the mean of samples. But as we know that we don't have the mean of samples, it will be the it's going to be the standard deviation of the population, which in this case is 15, divided by the square root of the sample size. The square root of the sample size is 30. So this is going to then generate the z-score for us. And as you can see, it has generated a z-score of 1.58 for us. Okay, so this is the z-score of the sample. Now what we have to find is this z-score so extreme that it falls beyond the critical point? In other words, does it fall in the region of rejection, or does it fall in the region of non-rejection? So just for visualization purposes, we'll also just make a line on this diagram so that we can represent it. But before that, let's calculate the critical point for 5% level of significance. So if we say that the level of significance is 5%, it means that the critical point will be somewhere at around 95%, right? It will be somewhere here in this region at about 95%, right? As you know very well that 95% can be represented numerically as 0.95, right? So we have two ways to calculate the critical point from here onwards. One way is that you can go to the z-score table, right? And on the z-score table, what you could possibly do is look at where does it turn to 95%. And you will see that the closest place where it can turn to 95 is the place where 1.6 and 0.04. 1.6 and 0.04. You will see that 0.04 is right here and 1.6 is here. So where do they intersect? Right, they intersect at 0.94950, which is the closest point to the 95%. This thing here, 0.94950, is closest to 0.95, right? So this gives us a z-score of 1.64, right? So you could calculate it like this, and you could say that your critical point for 5% level of significance is 1.64, right? Okay. So now that we have a 1.64, so let's go ahead and just look at this visualization. Let's say that 1.64 is this line. Let's say 1.64 is this line that we have here, that we've just drawn. Okay. And what we can also do is, just to make it simpler for us, we can just call it 1.64. Okay, there we are. All right, so basically the area that is beyond 1.64 to the right, this area right here, is the area of rejection, and anything on the left side is going to be the area of non-rejection. Now, where do you think 1.58 the z-score lies? You will see that 1.58 is to the left of 1.64. In other words, it's in the area of non-rejection. It's in the area of non-rejection. Since it is in the area of non-rejection, we will say that we failed to reject the null because it's in the area of non-rejection. So if I was to just make an arrow to kind of make it easier for visualization, this 1.58 is going to fall somewhere here, right? So let's give it a different color, right? So as you can see, the 1.58 is less than 1.64. It will fall somewhere here, right? This area is the area of non-rejection because it's less than the 1.64 mark, right? So this lets us know that we have failed to reject the null. And since we have failed to reject the null, we can infer that the IQ is indeed less than equal to 115. It's less than equal to 115 as the claim goes, as stated by the town council. So this is how the this is a practical application of how the z-test would run, right? Let's take a look at another example just to understand this better. So let's say we have another example here. And here's the example. A university states that boys on an average score 600 or less in an exam. The standard deviation of the scores is known historically as 100. The scores of, it's not 20, it's 30. The scores of 30 boys is collected randomly, okay? Why is it important that, I changed it? Remember that the z-test should be only run for 30 and higher, right? Because it's only at 30 and higher sample size that regardless of the original distribution, it will start taking on a Gaussian shape, right? Or a normal distributions characteristic. So in fact, you can check here that the sample size that we took here was actually 30, right? 30 or greater. So bear that in mind for a z-test. So we have the scores of 30 boys collected randomly. The level of significance is set as 5. Check if we can infer the university statement is correct, okay? So again, you start off with a sample mean. Your sample mean is what? Your sample mean is the average of these numbers. The number comes out to be 640, okay? What's the population mean? The population mean is the claim of the university that people generally score, or students generally score 600 or less. That's our population mean. The standard deviation is given as 100 basis some sort of historical knowledge that the university has. What's a sample size? The sample size is 30, okay? What's the z-score of the sample? So remember, the z-score of the sample is nothing but the value of the sample mean minus the population mean, which in this case is going to be 600, divided by the standard deviation, which is 100, divided by the standard deviation divided by the square root of the sample size of 30. This will generate the z-score for us. In this case, you can see the z-score is 2.23, which is fairly high. What is the critical point for 5% level of significance? Now remember that we had already seen in the previous example, it is 1.64, right? 1.64 is going to be the critical point for 5% level of significance, correct? Okay. So one keyword about this 1.64. If you recall, how did we find this 1.64? We found this 1.64 from the z-score table, right? We went in here and found out where was 95%. We found that the closest value to 95% is 0.94950, and we saw that this 0.94950 is at the intersection of 1.6 and 0.04. So that gave us the z-score of 1.64, right? Okay. Is this the only way? Do you always have to rely on this? Well, the good part is you don't need to. There's an inbuilt Excel function that we covered in our video on probability distributions. Just to remind you, remember that the couple of very important formulas. You have the norm.dist, which is one of the formulas which gives you the cumulative distribution and the point probability distribution as well, right? There's also a norm.inverse, if you recall, right? And the way that norm.inverse works is if you type in the Excel formula norm.inverse, you see it takes the probability. And if you recall, if our level of significance is 5%, then what is the remainder of the probability? So the remainder of the probability is 95%, which gives you the critical point, right? 95%, remember that we are dealing with a normal distribution. A normal standard distribution has a mean of 0. and the standard deviation is 1. If you utilize this, it gives you the critical point for the 5% level of significance as 1.64. Okay. What was the null hypothesis that we had? So the null hypothesis was that the score, the exam score of the university students is less than equal to 600, right? That was the hypothesis that we started off with. That's the claim of the university. Okay. What would be the alternate? The alternate would be that the score is not less than but greater than 600, right? That would be our alternate hypothesis. So let's make a note of that as well. Okay. So now let's mark this 1.64. So let's say that the 1.64 that we have here, we could just copy it from the previous example, or let's just mark it here. Okay, no challenges. So let's say the 1.64 is approximately here. Okay, so let's say this represents 1.64 on the distribution. All right, so let's make a note of it here, and we have 1.64. Okay, now what you'll notice is that the value of 2.23, the z-score of our sample is 2.23. So in reality, our sample kind of lies to the right of 1.64. In other words, what our sample is an extreme sample. Our sample is an extreme sample, and it falls somewhere here. It falls somewhere on the right side of 1.64. In other words, the sample is so extreme that we have trouble believing the starting notion, the null hypothesis, that the score is actually less than equal to 600. In this case, you will see clearly that the z-score lies in the region of rejection. In this case, given that the z-score lies in the region of rejection, we can now state that we can reject the null hypothesis. We can say that we can reject the null hypothesis. In other words, we can infer that the score is greater than equal to 600. We can conclude that the score is greater than equal to 600. Remember, we cannot say we have proved that the score is greater than equal to 600. Okay, so very important distinction to keep in mind. So this is another example of how you would go about using the hypothesis testing, or to be more precise, how you would utilize a z-test when your sample is 30 or greater, sample size is 30 or greater. Okay, let's take a look at a third example. Now, the third example again is, so let's say that a university states that the boys on an average spend $600 on their food, $600 every month on their food. Okay, let's say this is at a university. And this is the claim of the university, right? So this is the claim of the university. So remember that this will then become our null hypothesis. So what is the claim? The claim states that boys on average spend $600. Okay, this becomes your null hypothesis. All right. What would be alternate hypothesis? The alternate hypothesis now would be that the spending is not equal. Spending is not equal to $600. Correct? If your null hypothesis says that it is equal, the alternate hypothesis, or H1, will be that it is not equal. Okay. Now, in this case, what's the sample mean? So to begin with, your sample mean is, again, remember, the easiest to calculate. You just take the average of all of these and you have the sample mean right there. Okay. All right. What's the population mean? Remember, the population mean comes from the problem statement here, where the university is claiming that it is indeed $600. Okay. What's the standard deviation? The historical historical numbers or historical estimates by the university put the standard deviation as $100, right? So some people spend more, some people spend less. The standard deviation is $100, let's say. Okay. Now we come to the sample size. What's the sample size? We took this sample of 30 students. Okay, now what's the z-score? So in this case, the z-score again is going to be the mean of the sample minus the population mean of 600 divided by the standard deviation, the historical standard deviation of the population, and which is in turn going to be divided by the square root of the sample size of 30, right? So our z-score is 2.23. That's our z-score. Okay, what about the critical point for 5% level of significance? Before you answer that question, I'd like to remind you that in the last two examples that you just looked at, how many areas of rejection did you have? Because of the way the problem statement was formulated, the null statement was a less than equal to. You had only one rejection area, which was a higher value, right? In this case, your core statement is an equal, which means it's equal to 600. Now, how can something be not equal to 600? Remember that something can be not equal to 600 in two ways. By either being significantly less than 600 or being significantly higher than 600. So this problem does not have one rejection area. This actually has two rejection areas. So if you were to take a look at it, and if you were to visualize it, the right way of visualizing this is that we'll now have one rejection area which is to the right, anything to the right of this black colored line. And then you will have another rejection area, which is going to be nothing but anything to the left of this. So anything to the left of this line also is going to be a rejection area, right? So this problem has now two rejection areas, and that's going to be vital for us to remember. Now, what are the implications of having two rejection areas on the critical point for 5% level of significance? What it means for us is that this 5% that you just looked at can now be broken up into two parts. Which is going to be that on the right side, your rejection area will represent 2.5%, and on the left side also the rejection area will represent 2.5%. And what that means is when you calculate the z-score, you're going to go ahead with this number, right? So if 2.5% is the rejection area, what is my area to the left of this? So my area to the left of this 2.5% is 1 minus 2.50, which is 9750%, right? So if you go to the z-scores table, where do you have this 9750 percentage? So let's see, 97381, 97441, there you have 0.9750. This represents 97.5% of the area. And what is the z-score for this? The z-score for this is the intersection of 1.9 and 0.06. So in other words, your critical point for 5% level of significance in this case, because it has two areas of rejection, is not 1.64 anymore, it is 1.96. And this is what I wanted to talk about. Remember that basis, whether it's a single tail test or a double tail test, this is a double tail test, you have two rejection areas. Your critical point for the 5% level of significance will change. In fact, it's going to shrink the area of rejection on the right side, because it's now split between two areas, right? Having said that, does it change anything for us? Well, in this case, it doesn't. What you'll notice is that even if this point right here represents 1.6, even if it represents 1.6, the z-score of your sample is still extreme. It is at 2.23, and 2.23 is still going to lie to the right side of this. So it's still going to fall somewhere here, right? Regardless of the fact that your level of significance has caused the critical point to actually move further away to the right, your z-score is still in the area of rejection. What does this mean? It means that we reject the null. And if the null was that the spending was equal to $600, we can now conclude, or we can now infer that the spending is not equal to $600. In fact, it's on the greater side. So it's going to be higher than $600 on an average for the university. Okay. Again, remember, you're not proving it. You can just infer, you can imply, you can conclude, right? you can reject the null being spending is equal to $600. Okay, so this should give you now an understanding of how this works for a double tail test as well. Now moving on to another important concept, the concept is that of p-value. Okay, the concept is that of p-value. So you will often find that in hypothesis tests, people don't separately calculate the z-score, and they don't separately look at the critical point for 5% level of significance. In other words, they don't separately calculate these two and then compare if these are greater or less than each other. What people generally do is when they run a hypothesis test and they get a p-value, they look at the p-value, and if the p-value is less than 0.05, if the p-value is less than 0.05, they say that we reject the null hypothesis. And if on the other hand the p-value is greater than 0.05, they will say that they fail to reject the null hypothesis. So what exactly is this p-value? And remember that the p-value is a very misunderstood concept really. So here's what the p-value is. Okay, and we'll understand this with an example here. So let's say the same question that we solved about the average score being 600 or less, right? If we were to calculate the z-score, and we already calculated the z-score here, right? What was the z-score again? Remember that the z-score was 2.23. All right, so let's say for just making a graphical representation, let's say this thing here, let's say this thing here is 2.23. This thing here is 2.23. The z-score is nothing but all of the area which is to the right of this 2.23. So this area that you have to the right of 2.23 all the way from here till the end is the p-value. Stated more theoretically, p-value is the probability of any data point having the area of greater than whatever your sample's z-score is. So it's going to be the probability of ending up with a higher value than what you've calculated in your z-score. Okay, so all of this area here to the right, in this example, to the right of this represents the p-value. Okay, so how do we get this area? So remember that to get this area, if the overall area is that of 1, remember that for a standard normal curve, the area under the curve is 1. Okay, to get this area, all that you have to do is you have to subtract the area to the right of this red colored line, right? So to get the area of the to get the area that you have to the right of the red colored line, you have to subtract 1. From 1 you have to subtract the area to the left. So let's try and do that. So let's write it down. So what's the p-value? So the p-value is the area to the p-value is nothing, the area to the right of the z-score. Okay, so how do you get this area to the right of the z-score? The area to the right of the z-score is nothing but 1 minus area to the left of the z-score. Okay, so it's 1 minus area to the left of the z-score. All right, so having said that, what was a z-score in this example? So if you go back and take a look at this, is from example 2, your z-score was 2.23, right? So let's go ahead and write 2.23 here. Okay, so what does 2.23 represent in terms of area? How do we get that? Okay, now remember that in order to get the area from a z-score, you can utilize the norm.dist function. So let's calculate the area to the left of the z-score. So what is the area to the left of the z-score? So the area to the left of the z-score can be computed by using the norm.dist function. So we can do the norm.dist distribution function, right? What's the z-score? The z-score is 2.23. What's the mean? Remember, for a normal standard distribution, the mean is going to be 0. The standard deviation is going to be 1, right? And what do we want? Do we want the cumulative distribution function or the probability distribution function? Remember, you're trying to get the area, right? The overall probability. So the area will be given to you by the cumulative distribution function, because the probability mass function only gives you the probability of a specific point. Okay, so if you utilize this function, this is the value you get. So you can see that this is the area. 0.9871 is the area to the left of the red colored line. This area right here is this. So now to get the p-value, remember what's going to be the p-value? The p-value is going to be nothing but 1 minus this number, right? So the p-value in this case, as you can see, is 0.0128, right? Since this p-value is less than 0.05, right? Remember, when the p-value is less than 0.05, what do? We reject the null. So in this case, we can reject the null. This is another way by which you can make that connection as to what we are doing in the previous example. So when we are trying to understand hypothesis testing, we calculated the z-score then of the sample, then we checked if the z-score is more extreme. It's more extreme than your critical point, right? This check can also be conducted like this by calculating the p-value, and we have just looked at it, right? So this is another key principle for us to remember, that whenever the p-value as calculated here, and when you use different statistical softwares, you won't have to do all this. This is for your understanding. When you use statistical software or use programming languages to do all this, it will generate the p-value for you. All that you have to check is if the p-value is less than 0.05 or greater than 0.05, right? Less than 0.05, you will reject the null. Greater than 0.05, you will fail to reject the null. Okay. One word of caution here. Remember that p-value is going to be dependent upon your level of significance. This logic will only work when your level of significance is set as 5%. If your level of significance was set as 1%, then you would have a different treatment of this thing. Your p-value would then start taking on different values. So I see a lot of people making that mistake. It's something that we should be acutely aware of. Okay, and this is why the p-value concept works, because remember, ultimately what the p-value is trying to check is how much area is really there on the curve beyond the z-score of your sample, right? And if that value is small, that means your sample is extreme. If your p-value is small, it means your sample is extreme. If your p-value is large, that means your sample is not extreme and probably lying in the area of non-rejection. So this is the key concept that I wanted you to understand on this. Okay. So finally, to wrap up this video, remember that the p-value is generally preferred in statistical treatment over the concept that we looked at when we were trying to calculate two separate values. We calculated the z-score of the sample, we calculated the critical point, and then we compared them, right? Is not generally how you will see statistical tests being run. Most statistical tests only return a p-value to you. The reason it is preferred is because p-value represents a single value rather than dealing with two values. You're dealing with a single value. That's the usual reason for the preference. Also remember that usually, unless you change the level of significance in the statistical software, it will go in with a default of 5% as the level of significance, and then you're going to end up by doing that comparison of whether the p-value is greater than or less than 0.05. Now, how do we remember this? One very common way that you'll see across different lines is, this is how people remember. If p is low, null must go. Right? It's a very simple, very creative way of remembering. So whenever p is low, null must go. Null must go means null is rejected. If p is high, null is to apply, which means if p is high, then fail to reject the null because null still applies, right? This is how people generally remember it. I do remember one session where one of my colleagues has a far more creative way of going about this. And what they said is if P is low, null must go. So that kind of remains the same. If P is high, null is the guy. So that's another great way of remembering this. This is a memory trick for you to remember when you get the result of the p-value. One last thing that I wanted to talk about is that the z-test has historically been always taught to students, but it's not widely applicable. In fact, chances are very high that you'll never get to apply it. It's still an important tool and for us to understand hypothesis test, but it has some limitations and severe ones. If you remember the examples we looked at, there was always an assumption about the standard deviation of the population, and you might you might scratch your head to say that, you know, if I don't know the entire distribution of the mean of the samples, how on earth am I going to get one, the mean, and second, how am I going to get the standard deviation? And the answer is you can't, and that's why people would generally rely on estimates of standard deviations from their experience, from some sort of historical estimate, which is not going to be the best possible solution here. And that is why that's a key issue with the z-test. The other thing is, for the z-test to be run, your sample size has to be greater than 30, right? That's when the central limit theorem starts to kick in, and you can assume that you're going to run all of these estimates or calculations on some sort of a Gaussian curve. So those are quite severe limitations for the z-test. It's great to teach the concept. It's great to learn the concept in a simplified way. Industrially speaking, what you will apply is not the z-test. What you're going to apply is something known as a t-test or a t-distribution test, also known as student distribution. And we will cover that in another video of ours in the future, because the t-test is one of the most common tests that you will see within hypothesis testing. Okay, so that was a quick recap of what we covered today. Hopefully it was interesting, and you would have learned the basics of hypothesis testing and why it works from this video. Thank you so much for watching. See you next time.